Hi and welcome to Unit 1, Topic 3, Video 11. And in this video we're going to do a further example, we're on example 2 now, of proof by induction. And we're just adding a little bit on as we go. So let's have a read. A student is trying to recall the formula for the sum of cubes of consecutive numbers. She thinks it may be n cubed times n plus 1 cubed over 8, or maybe it's n squared times n plus 1 squared over 4. Show by counterexample that one is incorrect, and prove the other is correct by mathematical induction. So basically we're trying to prove is 1, remember sum of cubes, 1 cubed plus 2 cubed plus 3 cubed plus ... plus n cubed, is it equal to n cubed n plus 1 cubed over 8 or n squared n plus 1 squared over 4. So you can't remember which one, and we need to find out which one it is before we bother trying to prove it. It's a really good idea to make sure that before you do any proof by induction, it's either an obvious proof by induction in the exam, or you know which way you're going, because it can be a long proof to then find out that it actually doesn't work. So what I'm going to do is I'm going to look for a counterexample. I'm going to start reasonably small, but not super small. I'm going to start with the first 3 terms. I don't want to start with 1 because often 1 works straight away. And I don't want to start with 2, it's often there as well. I've got the 3 here, and it's obscure enough that it probably won't work for one of them. So, first of all, my left-hand side is equal to 1 plus 8, which is 2 cubed, plus 27, which is 3 cubed. And that's equal to 36. My right-hand side, option 1, so I'll call this right-hand side 1, is equal to 3 cubed, n is 3 in this case, 3 plus 1 cubed over 8, and 3 cubed, 3 plus 1 cubed is 27 times by 64 over 8. 64 over 8 is 8, 27 times 8 is 160, 216. It didn't work. So let's hope that right hand side 2 works, because it looks like we've already found our bogey. So this time we get n squared, which is 3 squared, times by 3 plus 1 squared over 4, and that's going to be equal to 9 times by 16 over 4, which is 36. So it looks like, by counterexample, her second one is the correct one, and now we just need to prove that's true. So let's start with step 1. In step 1, we're going to prove it's true for n equals 1. Now, I do have to do this, 1 and 2, but I've already got a starting point 3, and I could use that as part of my domino effect. But we'll do it for n equals 1. Left-hand side is equal to 1 cubed, which equals 1. And right-hand side is equal to 1 squared times 1 plus 1 squared over 4. That's equal to 1 times 2 squared over 4, which equals 1, which equals left-hand side. So that's worked. Now we're going to step 2, which is my simple assumption step. So I'm going to assume that it's true for n equals k. And that gives me 1 cubed plus 2 cubed plus 3 cubed plus ... plus k cubed is equal to k squared, k plus 1 squared over 4. Now, it's tempting here to do some multiplying by 4 or something like that, but just don't play with it too much, particularly as an equation. Remember, it's a proof, so you can't follow that whole do something to one side and then the other side process. Because it's a proof, we really have to be careful that we deal with left-hand side, right-hand side procedures. So now I'm going to prove for n equals k plus 1. So I get 1 cubed plus 2 cubed plus 3 cubed plus ... Now I always leave my k cubed still here, and then I add my k plus 1 cubed, and this should be equal to k plus 1 squared, k plus 1 squared over 4. And I know it doesn't matter, but in this case I'm going to be careful and use brackets again, just to make sure I don't make a mistake. Now I might be cheeky and do that process again, where I leave my right hand side in that nice form, and see if I can factorise towards it, which I suspect I might not be able to this time, but we'll see how we go. the right hand side is equal to k plus 1 squared, k plus 2 squared over 4, and the left hand side is equal to 1 cubed plus 2 cubed plus 3 cubed plus plus k cubed plus k plus 1 cubed. Now, of course, our problem here is that we've got a ... but we know that we fall back on the assumption step again. And we use that to cancel out our ... for what it's equal to. And so this is now equal to k squared, k plus 1 squared over 4. And plus k plus 1 cubed. So now I'm going to do that thing. I'm going to try and get to the right hand side so I can see k plus 1 squared twice there and k plus 1 squared cubed, so k plus 1 squared there as well. So I'm going to take that as a common factor and I get k plus 1 squared outside of k squared over 4 plus k plus 1. And now let's see where this goes. I'm going to bring that together as one fraction. I've got k plus 1 squared out the front still. And then I've got k squared over 4 plus 4k plus 4 over 4. And now I've got k plus 1 squared. Then I've got k squared plus 4k plus 4 over 4. Now keep in mind I've already got, and I'm going to do some highlighting here that you wouldn't normally do. I've got that, and I've got that. So this should be k plus 2 squared. And if I look closely at it, it is. So I get k plus 1 squared, k plus 2 squared, all over 4. Which is what I expected. I could see that there in my right-hand side. And so now I can make the statement equals right-hand side. And then I can do step 4, which is to conclude. And I conclude by saying, well, as I've shown that it works for n equals 1, then it must work for n equals 2 based on n equals k plus 1 working because n equals k worked. And as it now works for n equals 2, it must work for n equals 3. And as it now works for n equals 3, it must work for n equals 4, and so on and so forth until the end. So there's video 11 and a further example. And join us for video 12 where we do one more example of proof by induction. All the best.